So, hello all, good afternoon and welcome back to this tutorial session number 2, which will be a continuation of tutorial session number 1. So, we have taken a problem and we have solved it step by step, and we'll be continuing the same problem. Whereas here we will be looking at certain more aspects like estimating the total weight of the system, like envelope mass, gondola mass, fin sizing, and also we will be estimating the drag of a small remotely controlled airship using a empirical relationship available. So, brief intro about myself. I am KM Kiran Babu, speaker for the session. Right now, I am working as project research scientist at IIT Bombay and pursuing PhD in the area of LTE systems for Venus exploration under the supervision of Professor S. Pant. I have a total teaching experience of 8 years at other engineering colleges like ADCT, ASTA, and Karpagam Institute of Technology, Coimbatore. And following are my research interests, and you can follow more about me on my LinkedIn profile. So this is a brief intro about myself. Not wasting time, let us move into the tutorial session. So this is the design methodology that we are following. In the previous session covered by Saurabh Bagare, we have already estimated certain parameters. I would just like to recall some of them. So could someone answer me what is the payload of the system that we're designing now? What is the payload of the airship for which we're designing now? Students?
Envelope.
No. What is the payload? What is the payload for which we are designing?
Gondola.
No. What is our payload?
250 grams.
Exactly. So we are looking to design a small remote controlled airship for 250 grams. Okay. And you have already estimated the volume required. So what is the volume required? You have already estimated the volume required, right? So what is the volume required for this lifting this 250 grams?
So 1.403 meter cube.
Perfect. Okay. And what is the shape that you have chosen for this particular airship? What is the shape name called?
Ellipsoidal.
Okay. It's ellipsoidal?
Double ellipsoidal.
Are you sure?
NPL. Sorry.
No. Which one? Double ellipsoid, NPL. Okay. So what is your total area? What is the area of your envelope?
7.755.
So here, this is very important for us. We will be doing this calculation from the area actually. So if you look at this focus of this tutorial, we'll be looking at first will be envelope weight or envelope material selection and weight. For that, we need the surface area. So remember this 7.756 meter square, which will be our surface area of our envelope. So we'll further proceed in this. So first question I want to ask you is, so when you want to, so you have already, you have to design an airship for 250 grams. You know your shape. You have already.
Your voice is lagging.
I'm audible now? Is now clear?
Yes, sir.
Okay. So I'll do one thing. I'll remove my headphones. I'll directly use. Now am I clear?
Much better.
Okay. So I removed my headphones. Sorry for that. So the task before us is to we have a 250 grams payload for which we are designing this or sizing this remotely controlled airship, indoor airship, and we know our parameters of volume and petal sizes. So now we have to make a petal and we have to select a material for it. So what are the parameters that you will look into for selecting envelope material? What are the features that you look at? Can you guess or can you recall from yesterday's session? Anyone?
Lightweight, high tear strength.
Correct. So lightweight is GSM. We need to look at GSM. GSM stands for grams per square meters. So tear strength, permeability. What do you mean by permeability? What do you mean by permeability?
Able to pass through.
Able to pass through of helium or hydrogen, correct? Then flexibility and sealability. These are the 5 features of the envelope material that we need to consider while selecting the material for our envelope. So would you prefer a larger GSM or a lower GSM? Would you prefer a material with higher GSM or a lower GSM? What do you prefer?
Lower.
Lower GSM. What about permeability?
Low permeability.
What about tear strength? What about tear strength? Of course, high tear strength. So we look at these following features: lower GSM, higher tear strength, lower permeability, higher flexibility, and higher sealability. So these are the 5 features we look at deciding a envelope material. So there are many materials out of which we can make
So,
envelope or airships.
So
For
what is sealability?
sealability is how good it is able to seal. Like, see, we make petals and we use sealing method, hot sealing method or RF sealing methods to join them. Okay, so they should be able, they should have a good sealability. They should be able to quickly join together with some kind of sealing technique we use. Like weldability. Did I answer your question?
Yes, sir. Thank you, sir.
Okay. So there are many materials of which are generally used for making airships or LTS systems. So what you see on the screen are the most suitable materials that we use in our lab for making indoor airships. So the first one is metallized polymer. Its GSM is 65 GSM or it's available in 150 GSM. Then we have PVC coated nylon. Then we have PVC at different GSMs. These are the most used materials in our laboratory for making indoor airships. So for this tutorial, we are going to choose a material called metallized nylon and its GSM is 65 GSM. Note down this number. So the material that we are going to use for calculation purpose is metallized nylon and its GSM is 65. Note down the value 65 GSM. This particular material has good flexibility, strong, durable, low permeability to gas, lightweight, and it's a heat soluble material. So in my course, when I was doing this course, we did experiments using this particular material. It's a very good material and it is a material which is easily handleable. And we are going to use this for our tutorial session today. So what is the area of envelope we have? What was our envelope area? It was 7.76. Correct. So the material that we are using is metallized nylon and its GSM is 65 GSM. Okay. There's something called factors for joints and patches. See, when we make our envelope, we actually make it with help of some kind of joint, maybe lap joint or a kind of joint. So when we make joint, we will have some additional material which will be cut for making the joint. So we call it as additional or penalty for joints, and we'll put some patches on the envelope to connect it with some tether or to connect with some gondola or to hold it or to handle the envelope. We'll have some patches made on the envelope. So for these patches and joints, we consider 15% as the factor of weight. 15% of weight is considered as additional weight of the envelope material. So we multiply it with 1.15. So this 15%, whatever the value that I am saying to you, is arrived based on our experience in the lab. it is a variable parameter. It can vary plus or minus 5. It depends on what kind of joint you are using and how many patches you are putting. As a first estimate, we will go with 15%. So the factor is 1.15. So the total weight of the envelope will be 1.15 multiplied by total surface area into 65 GSM. So can you quickly make this calculation? Give me the answer now.
579.76, sir.
579 or 580, we can keep it.
Yes, sir.
Okay, so this is our envelope mass. So we have now estimated the envelope mass. So we had our payload is 250 grams. To carry payload, we need an envelope material, and envelope material's weight is approximately 579 or 580 grams. Okay, so we now know our envelope weight with weight penalty of 1.15, that's 15%. So this is an example of finished envelope, and you can see there are some patches there, and you can see some extra allowances for finishing it. Okay, there will be a backside, there will be a vent for filling the gas. So these are the things that we take in additional for adding that 1.15. So now envelope will be fitted with something called gondola. What is gondola?
The part where payload and cockpit is located.
So it's an indoor airship. So it's a bay where we have payload and other all electronics, battery, our motors, and all our instruments will be holded in that device. So this is an example of gondola. Typically, gondolas are made up of different materials, like people use bamboos, balsa woods, carbon fiber rods, styrofoams, plastic sheets. Okay, so they use different kind of materials. Okay, whereas the recommended materials would be like corrugated sheets, like high density polythene sheets, which can accommodate our avionics and other payloads. So the size of the gondola should be such that it should be as small as possible, but it should fit our instruments and equipments required for safe handling of the airship in a sufficient amount of box. And it can be connected to gondola with some kind of ribbons like this. You can see some kind of ribbons there. We can connect it with some kind of a ribbon around the envelope. So in this tutorial, we'll do the mass estimation of gondola. For estimating the mass, let us assume that gondola is made up of high density polythene sheets, a kind of sheet which we typically get in our shops, which are very high density materials. Okay, so they'll have a very good sheets. So Woodska density, so we assume it to be 20 kg per meter cube. Okay, so its density is 20 kg per meter cube. And let us consider that our length of the gondola will be 0.26 meter and width is 0.25 and thickness of 0.05. So if you want to make a gondola of this size with a material of 20 kg per meter cube density, so the mass of the gondola comes to be around density multiplied by volume. So can you do this mathematics and give me the answer? Yeah, 65 grams. So now our gondola weight is 65 grams. So make a note of it. If you compare it with our film or envelope mass, like envelope material was 65 GSM. That is 1 square meter of envelope material is added as the gondola mass. It's 65 GSM and is 65 grams. Okay, so gondola mass is 65 grams. Now remember that gondola will also hold the motors and other avionics bar, and to hold motors we may need some fixtures for holding the motors. These things will be added in the envelope, and this envelope or this motor mass estimation will come later. Okay, so remember that point, which will be added in this at the later stage. Okay, so now we have estimated our envelope mass. What was our envelope mass? Envelope mass.
579.73.
Yeah, 509 grams approx. And gondola weight was 65 grams.
Yes, sir.
Am I right?
Yes, sir.
Now we will move towards fin. So we look at two things now. First is sizing of the fin. The other one is estimating the weight of the fin. So I hope you can recall this table from yesterday's session, where the different fin sizing parameters and their values are given. And can you recall where does these parameters come from? How does these parameters are arrived at? How did we know the area ratio is 0.594? How did we get these values?
Sir, maybe they were the experimental values
No.
based on the literature. Sir.
Answer is on a slide. You can see the answer from the slide. Not from experimentation. Several existing indoor airships were studied. So we study different existing airships and we take the area ratios of them and we take an average of their values, and that's how we arrive at these values. Okay, so the first one is area ratio, that is S fin by S envelope. S fin stands for total area of the fin area, total fin area by total envelope area. Then we have aspect ratio. And why do we have 4 there? In aspect ratio, there's a parameter multiplied with 4. What is that 4?
Sir, because we have 4
Control
fins.
surfaces.
4 fins. Aspect ratio is fin span square divided by surface area of fin. As there are 4 fins, then we have multiplied it with 4 and its value is 0.6585. And we have span to chord ratio, taper ratio, and location ratio. What do you mean by location ratio? What do you mean by location ratio?
Sir, it will help us to determine the location of the fin on the envelope.
No, so how do you define it?
Length of fin divided by length of envelope.
No, not length of fin. The location of the leading edge of the fin from the nose of the envelope. What is the position of its leading edge to the total length of the envelope? So it's around 80%. So at the 80% of the total length of the envelope, we have our fins. So it's at the trailing edge of the envelope. That is the meaning for us. So I request you people to just take a snap of this because we need these values for our calculations. I'll give a minute time to take a snap or note down these values. Area ratio, aspect ratio, span to chord ratio, taper ratio, and location ratio. Note down these values or take a snap of it. If you say go ahead, I'll proceed. Can I move forward?
Yes, sir.
Hope you have taken a snap or you have noted down these values because we will be using these values for our sizing the fin and estimating the weight of the fin.
Yes,
So
sir.
first we look at fin area estimation. So for estimating the area, we'll use fin area ratio. Fin area ratio is, what is the value of fin area ratio?
0.0594.
Correct. So we have our envelope area. Envelope area we have estimated is 7.756. As we have envelope area, we know our area ratio. So we can calculate fin area. S fin area is S envelope into area ratio. Am I right?
Yes, sir.
So what will be the S fin now?
0.460, sir.
0.460. Just calculate it. Okay. So next we have our span. We need to calculate our fin span. So we can calculate fin span with our aspect ratio of the fin. So using the relationship,
0.275.
what is the span we get?
0.275.
2754.
0.275.
2754. You just calculate and keep it. I will just check the values. Then we have root chord. So we need to calculate root chord. So we have a span to chord ratio. So from this, can we calculate root chord?
0.4896.
Then using taper ratio, we can calculate the taper ratio. So we know the we know the taper ratio and we know the root chord. So we can calculate the tip chord. Right?
0.346.
Okay. Now our objective was to calculate our fin area. We need the area of fin, each fin. So now we can use trapezoidal area formula to calculate area of each fin. The area of each fin will be half into length into root chord plus the tip chord. Like typical formula we use for calculating the reference area of a wing, the trapezoidal formula. So we know our root chord, we know tip chord, we know our span. So using these relations, can we calculate area of each fin?
0.1151.
1151 or 52?
Yes, sir. 0.1152.
So if you have done all these calculations, so S fin is 0.4607, span is 0.2754 meters, root chord is 0.4896 meters, approximately 0.5 meters, that is 50 centimeters. Tip chord is 3468 meters, 0.3468 meters. Then we have our area of each fin is 0.1152. So now we know total fin area and area of each fin. Okay. So we have estimated the size of the fins. Now we will be looking at estimating the weight of the fin. What will be the fin weight? So for estimating the fin weight, we'll assume that fin is made up of a material whose GSM is 250. It is made up of a material which is having a density of 250 GSM, and total fin area is 4607. Each fin area is 0.1152. So total fin area is 4607. Am I right?
Yes, sir.
So now how do you calculate mass now?
Rho
How do you
V.
sorry?
Mass is
Density into
equal to rho
volume.
V.
No, density into GSM. It's not volume, it's area actually. We have GSM here. It's gram per square meters. Okay. So we multiply these values and we add 10% extra penalty we added because we will connect this fin to envelope using some kind of technique. Either we use velcros or some ropes or some mechanism we use to connect this fin with the envelope. So for that we add 10% as weight penalty. So we multiply it with 1.1. So if you substitute this relationship in the values, I mean values in this relationship, 1.1 into 0.4607 into 250. What's the value we get?
126.69. 120.69.
Okay, yeah. So now, what are the weights we have estimated? Our payload is 250 grams. So to lift 250 grams payload, we need an envelope. What is our envelope mass?
Uh, 579.7.
Okay, 579 approximately. Then what is our gondola mass?
65.
65
65
grams.
grams.
What is our fin mass? 127.
Yes, sir.
Yes, sir.
Okay, so we have estimated our envelope mass. We know our payload. We know our gondola mass. We know our fin mass. I think we also know our amount of lifting gas, right?
Yes, sir.
Correct. We have also estimated amount of lifting gas. So we just need our estimate of motors. That is the propulsion system, which we'll be doing it in the tutorial number 3. So we have done mass estimation of most of the components in this particular design. Okay. Now to estimate the thrust, to estimate the weight of the motors, we need to know the drag value. So only when we know what is the drag produced by or what is the drag experienced by this airship, we can select or we can decide what kind of motors we need for powering it. So this logically takes us to our next section, which is on drag. So if you observe the design methodology, once we know our fin weight and fin sizing, we next move towards drag. So actually, to estimate drag, there are many techniques available. What you can do is, once you know this initial informations, you can create a small CAD model in any CAD tool you know. You can do a CFD analysis. From the CFD analysis, you can directly compute drag. It's a very little complicated technique because you have to make a CAD model. Then if you put all these fins and all, then the grid size becomes very accurate, and you need to do lot of computational resources for doing this task to estimate our drag, which will make this conceptual design process little bit complex. So in this tutorial, we will be looking at a simple empirical formula to estimate the drag of a given airship. So using that empirical relationship, we'll estimate the drag. Once we know the drag, we know our thrust requirement. From the thrust requirement, we can estimate the size of the motors and other avionics based on that. So we'll now move into the section on drag computation. So before I begin, I would like to ask one question to you. Suppose as a student, if I give you a spherical ball of say 10 centimeter dia, how do you estimate drag of this spherical ball? I'm giving you a ball which is having a spherical ball of 10 centimeter dia. How do you estimate drag experienced by this?
By knowing drag coefficient.
Sorry? Can you come again?
With the help of drag coefficient.
Okay, if you know drag coefficient, you can directly substitute in the formula and you'll get it. So, but how do you get the drag coefficient? Where do you get this drag coefficient from? How did you estimate this drag coefficient?
By knowing velocity.
You need the drag coefficient, right? How did you get the drag coefficient?
D upon half rho V square S.
With the help of
So-
drag formula.
No, that's what I'm saying to you. So to estimate the drag coefficient, you need to first measure the drag. If you know how to measure the drag, then there's no need to have this drag. See, there's a contradictory statement. So how do you do this?
By knowing thrust.
We have a device for that. We use in our labs. What is that equipment called? How do you measure drag of a given body to you?
Venturimeter.
How does venturimeter measure drag? wind tunnel.
Yes, sir, wind tunnel.
Using wind tunnels, we can measure the drag. Okay. So coming to this topic of what we are going to discuss, see, there is something one needs to very clearly understand. Drag coefficient. Typically in our aeronautical engineering, we use area normalized drag coefficient. So what we do, we take a wing or we take an aircraft, we put it in a wind tunnel and we measure the drag, and we divide the drag with dynamic pressure of rho v square, and we divide it with the area. The area we take it as the platform area of the aircraft, B into C or B into C bar, whatever it is. We take the platform area and we divide it with area, and we normalize this value with no dimensions, and we get a parameter called as coefficient of drag normalized with area. So we call it as drag coefficient normalized with area, or simply speaking, drag coefficient. Whereas in LTS systems, we don't use area normalized drag coefficient. Instead, we use volumetric drag coefficient. What is volumetric drag coefficient? Here, the normalization is carried out by volume, not with area. So it is drag divided by dynamic pressure into volume power 2 by 3. This volume power 2 by 3 comes because to have a dimensional balance and to cancel the unit so that CDV does not have any unit. Okay. So in LTS systems, we use this particular volumetric drag coefficient. This is very, very important because when you use any CFD tools for drag estimation, you typically make a mistake of calculating with the help of area. Whereas what we particularly need is volumetric drag coefficient. And we have a technique to find out the volumetric drag coefficient once we have our area drag coefficient. So we can find out our area drag, volumetric drag coefficient once we know our area drag coefficient by multiplying it with 3 by 3 into L by D power 1 by 3. So using this relation by Young's relation, we can calculate the volume drag coefficient of a given body once we know our area normalized drag coefficient. Okay, so this is to be kept in mind. In all the LTS systems, when we use calculations, wherever we have drag coefficient, we will be using volume drag coefficient or volume normalized drag coefficient instead of area normalized drag coefficient. This is something to be remembered. Now coming to this tutorial, we will be using this formula, this famous formula called as Horner's formula. This formula gives us the estimate of a preliminary estimate. Actually, it will not give an 100% exact estimate. There will be an error of around 10% to 15% in its calculations. But this formula is fair enough to start the calculations in the conceptual design stage. So it's a complex formula. I request you people to take a snap of it and keep it with you, because we will be using this formula for our calculations. If you closely observe this formula, here input is the fineness ratio and Reynolds number, L by D and Reynolds number, and we get a drag coefficient. So whatever the shape it is, let it be GNVR shape, if it NPL shape or Xeon shape, whatever shape it is, it's immaterial. It is going to give you the same drag coefficient value for the fineness ratio. Okay, so that's why it's called as an empirical formula. It's an initial estimate. It will not give you the 100% exact value of CDV with your experimental results. So there will be an errors there. So we will check it now. So before we proceed with the calculations, let us check this Horner's formula with the values we know. So there is one airship called Xeon 1 airship. Okay. In the Xeon 1 airship, the coefficient of drag volume, the volumetric drag coefficient is 0.029 at Reynolds number of 7.3 million. That is 7.3 into 10 power 6. And Xeon 1 airships L by D is 4. So in this formula, you substitute L by D as 4 and Reynolds number as 7.3 into 10 power 6. And what is the CDV value you get? Can you calculate and give me the answer? Can you calculate this? L by D is 4. Reynolds number is 7.3 to 10 power 6. What is your volumetric drag coefficient? Could you calculate?
Yes, sir.
Yes,
So what
sir.
is the answer you got? Are you getting? Actually, answer is available on screen. I just want you to get used with this formula so that you will be using it in the next step. Remember, it is D by L in the second and third substitution of the equation. It's not L by D, it's D by L. So did you get it?
Wait a minute, sir.
Okay, take your time. Because this is the next step. We'll be using this. You should be getting it.
0.024
0.024
7.
247, which is approximate as 0.025. Matlab you can see closely matches.
Yes,
So the
sir.
match percentage is around 13.8%. So there's an error basically. So the Honors formula is not going to give you 100% correct result, but it will give you the first estimate to do it. Okay. So in the conceptual design stage, we need that value, because once we go through the conceptual design, in the detailed design, we can go for a more accurate estimation of this particular CDB. Okay. So we'll be using this Honors formula for our estimation. So to use this Honors formula, we need to first calculate our Reynolds number. So what is the length of our envelope?
3.5 meters.
Actually, the requirement was it should be less than 4 meters, right?
Yes, sir.
The requirement said it should be less than 4 meters. So we are saying, okay, let us design it within 3.5 meters. It's our assumed value. So the velocity was 8 meters. The requirement said velocity should be 8 meters per second, right?
Yes, sir.
Okay. So how do you calculate a Reynolds number if you know these two values? What is the formula to calculate Reynolds number?
Rho VL upon mu.
Okay. So, or it is VL upon nu.
Sir,
Right.
we don't know the coefficient of dynamic viscosity.
No, I'm giving you kinetic. So your nu by rho, I'm giving you kinematic viscosity directly. Kinematic viscosity at sea level is 1.46 into 10 power minus 5 meter square per second. Dynamic viscosity divided by density is given to you now. Right?
Yes, sir.
So Reynolds number will be VL by nu.
Yes, sir.
Okay, so what is the Reynolds number now? Try to give it to me in 10 power 6 in millions. Try to give the answer in 10 power 6. 8.0 into 3.5 divided by 1.46.
19.17 into 10 raised to 5.
No, give it in 10 power 6.
1.917 into 10 raised to 6.
1.91 into 10 power 6. This is the
Yes,
Reynolds
sir.
number. So we know the Reynolds number now. We have estimated it. Okay. So you know Reynolds number. To estimate CDV, so let us take the fineness ratio to be 4. L by D to be 4. Okay. So these are in blue color, which are our assumed values. So our values which are assumed. So we know our Reynolds number now. Substitute this Reynolds number and L by D in the Honor's formula and compute the volumetric drag coefficient of our model or our design. So L by D is 4. Reynolds number is computed. Calculate the Reynolds, volumetric drag coefficient. And give me the number. What is the value?
Sir, wait.
Yeah. Do it carefully.
0.0309.
0.03097. Fine. So
Yes,
this is
sir.
our first estimate of our drag coefficient. Okay. For the design what we are making. So when we know now volumetric drag coefficient, CDV, what next? What should we do now?
Drag.
What should we do? We have to calculate our
Drag.
So what is the formula for drag calculation?
CD upon half rho V square A.
CD upon Q आएगा. So we know velocity, we know density, we know envelope volume, we know CDV now. The formula for drag, volumetric drag coefficient. Remember, it is not area drag coefficient, volumetric drag coefficient. So drag will be half rho V square dynamic pressure into volume power 2 by 3 into CDV. So we know volume now. We know CDV now. Substitute the values. Density is 1.225 sea level and velocity is requirement of 8 meter per second. So substituting that, we get envelope drag. What is the value of envelope drag? So remember the formula for calculating the drag of the envelope. So when we are using volumetric drag coefficient, it has to be volume power 2 by 2. 2 by 3.
1.52.
1.5214.
1.5224 Newton. Okay, third decimal there may be changes, but the answer what we have obtained is 1.5224 Newton. So this is the drag experienced by the body. Okay. Envelope drag. So we multiply it with 2. Do you know why?
No, sir.
Because this is only by the envelope. We have gondola, we have fins, we have other attachments to the system, right?
Yes, sir.
Only envelope and we have other attachments. So to take into account of those parameters, we multiply with factor 2 and we get total drag of 3.0447 Newton. So this is the total drag, which is nothing but the thrust requirement. So when you convert it into grams, we get it as 310 grams because we convert Newton to grams, right? How do you convert Newton to grams? How do you convert Newton to grams? Drag is 3.043 Newton. How do you convert it to grams? Force is mass into, or weight is m into g. So we divide it with g, we get into kg. Then we convert grams, kilograms into grams. So we multiply with 1000. So 3.43 divided by 9.81 into 1000 will give you 310. Check it. Am I right?
Yes, sir.
So remember the technique to convert it into grams, Newton to grams. We divide it with 9.81 and multiply it with 1000. So we get it in grams. So the total thrust requirement is 310.40 or 310, approximately 310 grams. So we need to choose a propulsive device, motors with propellers, which can produce minimum of this much amount of thrust. Then we'll look for the battery requirement for that motors, the avionics systems. So that will be covered in the next tutorial session. Okay, so summarizing this tutorial session, what we did is we took the input from our previous tutorial session, that is the envelope area. From the envelope area, we calculated the envelope mass. Then we calculated the gondola mass. Then we made the sizing of the fins. Then we estimated the fin mass. Then we estimated the volumetric drag coefficient. From the volumetric drag coefficient, we estimated the drag. From the drag, we estimated the required thrust for the further design process. So there ends this particular tutorial session number 2. So we are on time. So as we have a few more minutes, like another 10 minutes we have time, I would be happy to answer if there are any queries. So this is a summary of what we saw in this session as of now.
So can you define fineness ratio?
That is nothing but the length of the envelope by diameter.
Sir, envelope length and diameter.
Yeah, I'll show you envelope just a minute. See, this is the length of the envelope, the longitudinal length to the diameter.
Okay, sir.
That is fineness ratio.